All right. Well, hello. Happy Monday. Happy week 10. Happy December. It's December now. And yeah, this is our last week of this class. And yeah, for some of you, this will be like the last time. Well, not today, but this week will be like the last time I see you guys. I don't know. Some of you will. I guess I'll see you at graduation, but but after that, I don't think we have classes together. Anyway, let's talk about the final exam. So that's this Friday, right here, 8 a.m., bright and early. So I don't want to get in trouble for saying this, like in trouble from you guys, okay? So I've decided no calculation questions, okay? It's just gonna be like open-ended, short answer, like conceptual questions, okay? So it'll just be some conceptual questions. They should be fairly, you should be able to answer them fairly quickly. Like, I'm not looking for big essays or paragraphs. I'm looking for maybe 2-sentence answers, something around there. And we'll cover basically content from weeks 1 through, maybe I should even just start at like weeks 1 through 8, like up through like hierarchical Bayesian models, with the, in Gibbs sampling, okay? Because week 9, I started introducing a hierarchical document clustering model, which we will finish up today. And yeah, it'll be, I'm looking at something fairly short, maybe two pages, okay, of like 2 or 3 questions on the first page and 2 questions on the second page. And we're looking, maybe around 5 questions total, okay? And you'll have, 50 minutes to complete that. So no calculator, you can bring a calculator, but it's not necessary, okay? So there's not going to be you're not going to be doing multiplication and, working out stuff, okay? I'm not going to have questions on JAGs, things like that, and you can have a sheet of notes with writing on the front and the back. It's mostly going to be kind of conceptual. So just to give you an idea of like the level of conceptual questions, I just have a couple examples here, but obviously I'm not going to put these ones on the exam here. Okay, so what's the fundamental, or what are fundamental differences between frequentist statistics and Bayesian statistics? And the answer I'm looking for there would be something, I put my answers on the next page, but something along the lines of, in frequentist statistics, your unknown parameter is an unknown but fixed value, whereas in Bayesian statistics, the unknown parameter is an unknown random variable that has its own distribution. Okay, so that's, what did I write? In frequentist statistics, the parameters of a model are treated as unknown but fixed constants, estimated from the data alone. Bayesian statistics, the parameters of a model are treated as a random variable, estimated by using a prior distribution along with the data. Okay. What do I have? Okay. Briefly explain how Monte Carlo estimation is performed to estimate the expected value of h of x. That is expected value of h of x, where x is defined by the PDF of f. Assume we're able to sample from the PDF f of x directly. And then so here, you would just draw a bunch of random variables from f of x. You'd plug those values into that function h of x, and then you would take the mean. All right? So that's what you would write. Okay. I don't know. All right. So anyway, just some examples, and that's it. So I'm looking to, my intention is that this is like I don't know, a little bit easier and less stressful. I don't know. Sometimes I have these ideas of like, this is going to be less stressful, and then it just causes more stress to the students. So that's not my intention. I'm hoping that by, I don't know, I guess just having some open-ended conceptual questions, you can kind of focus on bigger picture concepts rather than getting caught up in all of the little nitty-gritty details. I guess the hard part of this is it'll cover from weeks 1 through 8, 9, somewhere in there. So, and then that's it. So that's this Friday. And I don't know. In the past, when I told students I would do like some open-ended questions again, for those, students came up with some questions, and you can put them on Campus Wire and kind of answer each other's questions and stuff. Make up possible conceptual questions to put up there. Okay, any questions about that? All right, and that's it. So Friday will be our final, and then nothing next week, okay, at least for this class. So that's that, okay. All right, let's get on with, I guess, today's content. So we are looking at a hierarchical document clustering model, okay? And this is based on this article, Gibbs Sampling for the Uninitiated, which I recommend that you read. And I started describing this, and the idea here is you've got a bunch of documents, okay? Documents being, could be articles or are basically text, okay? And it could be, shorter documents. I wrote tweets. I guess that word is disappearing. We call them posts now. I don't know. Or anyway, and you can have longer documents, newspaper articles, book chapters, things like that. And again, this is unsupervised learning, meaning we don't have like the answers already for us to kind of check our own accuracy. So in supervised learning, you have documents and they're labeled already, and then you kind of run them through your classifier, and then you can measure an accuracy. You can say, hey, you classified this document correctly, and you classified this document incorrectly. This is unsupervised learning, and we are trying to form clusters. We don't have answers. We're just trying to say like, hey, I want you to sort these into 2 groups, okay? And based on how similar they are, and we want to put some documents over here and other documents over here, and we don't have answers. We don't know if this one should be in cluster A or cluster B or something like that, okay? But that's what we want this algorithm to do, is that it's going to try to read these documents and try to group similar documents together. So we don't have any predefined clusters, so the algorithm has to kind of discover the clusters on its own. And what we do need to do is we need to specify how many clusters to search for. So we're going to start off with just kind of looking for two clusters. And so document clustering, this kind of unsupervised, it's a harder problem than document classification, because in a supervised learning with classification, we can say, I know I'm looking for these 2 topics. I'm looking for documents on sports, and I'm looking for documents on politics. And I know these articles, fall in this category, and we can kind of sort them, right? So this is kind of how we're working through the thing, and we've got, and let me pull up the article as well. So you have all of this kind of notation. These are all of the different things. So this kind of big C is our corpus. This is all of the documents that we have, okay? And as we kind of work through, we're going to start clustering them, and we're going to just kind of say this document might be belong to cluster 0 or cluster 1, okay? And so we have label 0 and label 1. And so we have the corpus 0, that's going to be kind of all of the documents that are currently in this pile, the labeled 0 pile. And we have corpus 1, and this is the pile of all of the documents labeled 1, okay? We have C0, which is just the count of the documents labeled 0, and the C1, the count of the documents labeled 1. So that's these letters right here. The set of all documents labeled X, the set of all documents is that, so the set of all documents labeled 0 or 1, and then the number of documents labeled 0 or 1 right there, okay? And when we talk about documents here, we're treating this as a bag of words model, okay? And so again, the idea here is you've got this piece of paper with words on it, okay? And then just kind of like in a cartoon, just imagine the words on this page. You know, you give the paper a shake, and then the words on the page just kind of fall as if they're little, they're little objects, okay? And you collect them in a bag, right? And so in the bag you have these words, and really, once you have a bag of words, then there's no order. There's no order to the words, and there's some major limitations because now that you have no order, it's just the counts of the words, and so you'll have documents with you could have documents with different meanings, but they have the same representation when you use a bag of words model, okay? So, for example, a document could be as short as basically, a sentence, right? And here I have two sentences. This one says, I am not upset, I am happy, okay? And this one says, I am not happy, I am upset. And the bag of words representation for both of these documents are exactly the same. Basically, it would say that am shows up twice, happy shows up once, I shows up twice, not shows up once, and upset shows up once. And that would be our bag of words representation, or basically you take the words, I guess we sorted them in alphabetical order, and we just said how many times does this word appear. And even though these two documents have opposite meanings, they have the exact same bag of words representation, so they're going to get classified as exactly the same, okay, or clustered as exactly the same because their numeric or vector representation is exactly the same. And so this concept of how do you take text and turn it into a numeric representation is this concept of vectorizing your text, okay? And so basically this has been we are turning this document into I guess a vector representation. And so right now this is in 1, 2, 3, 4, 5, I guess a 5-dimensional vector. Now traditionally, I don't know, depending on how many words exist in your vocabulary, let's say you're going to allow for up to like 10,000 different words, then each document would have a vector representation of dimension 10,000, okay? Because, and most of those will be zeros, right? Because like most documents aren't going to use the word, I don't know, aardvark and going from alphabetical order, it's not going to include, zebra and xylophone and things like that. And a lot of these documents will just have, especially if it's a short document, there might only be like 5 words that actually carry a value, okay? And everything else will be zeros, but still, it's got this big representation. And so the bag of words model is one way to vectorize text into a numeric representation. You have other ways to vectorize, and so if you wanted to do some kind of AI stuff with large language models, you have a choice of different kind of like vectorizers of different kind of ways to go from text into a numeric representation, and some of those will try to include information about the ordering of the words. You might look at like kind of what we call 2 grams, 2 words at a time, or something like that. But anyway, we're going to just keep it simple. Bag of words is among the simplest ways to vectorize a document. It's just how many times does this word appear, and you have basically a column for every single word that exists in your vocabulary. Okay, and so the bag of words it works really well if there's a strong link between the words itself and the subject or the topic. Okay. Okay. So this is how our document creation model kind of looks like. Okay. We have documents with 2 possible classes. It can either be class 0 or class 1. So this is how we're going to produce our documents, okay? And this is, okay. So when we say a document generation model, we are talking about a fake, simplified representation of, do we have a system that can explain the data that we're seeing, okay? Obviously, the way people create documents and stuff is somebody sits and they think about what they want to say, and then they type it out, okay? But how do we, but then, when you vectorize it and you turn it into just these kind of numbers, and something like that, do we have a simplified representation for what that kind of work looks like, okay? And the idea here is, we're flipping a coin, okay? And whether it lands heads or tails or whatever, 0 or 1, is going to decide, okay, today I'm going to write a document about sports, or today I'm going to write a document about politics, or something like that, okay? And if the class is 0, okay, and I'm going to write a document about sports, basically, the words I write, some of these words are going to have higher probabilities, okay? And we're going to basically generate the words that appear on the page, okay, or the words that appear in our bag, using a multinomial thing, okay? And so again, a multinomial thing is kind of like, you imagine either a die with a bunch of sides, or a wheel with a bunch of, partitions into it. Or another way you can think of it as like, a big jar of like M&M candies, okay? But every single one of these pieces of candy has a different word on it, okay? And depending on whether you have the jar labeled sports, and you have the jar labeled politics, okay? And in the politics jar, the M&M candies, you have more words like senator and president, okay? And laws or whatever. And then in the sports jar, more of these candies have the words like team and player and ball and things like that. And so the idea here is, depending on whether you have class 0 or class 1, we have, a lexicon, okay? Basically a listing of all of the words in our vocabulary with different probabilities assigned to them. And the probabilities will be different based on, the class. So I guess here, class 0, I have your document is about fruits, and class 1, your document is about sports. And so if it's about fruit, the probability for apple might be much bigger, 0.015, and banana 0.018. These are exaggerated because everything's usually on the order of like 10 to the minus 6 or 10 to the minus 5, okay? But you might have apple at 0.015 when it's about fruit, and ball will have probability 0.0001, okay? Whereas if it were a document about sports, apple would have a probability of, say, 0.0001, a low probability, but ball has a probability of 0.016, something much higher, okay? And it's just, you might have a vocabulary of, say, 10,000 words, and basically all of these probabilities, all 10,000 of those probabilities would then add up to 1. So, you can imagine all of these things being, really small, on the order of 10 to the minus 5 or things like that, okay? And basically we're saying, once you flip this, then you have a kind of a multinomial system, or basically you're just reaching into the jar, grabbing a handful of these M&Ms, and then you look at all of the words written on these things, and then you count, okay, this is, the word ball showed up 6 times, and the word goal showed up 3 times, and the word, senator showed up once. I don't know, because there's the Ottawa Senators. That's a hockey team, right? Okay, I don't know, but right. So it could be a document about sports where the word senator shows up a bunch of times. But do you call the players? You call them players, right? We don't ever refer to sports players. I don't know. It feels a little strange, right? You call them athletes. We will. Yeah. Okay. Okay. All right. So okay. So this is kind of how our thing goes. All right. So the binomial distribution is basically you're looking at the counts of 2 things, and the multinomial generalizes to more than 2 categories. You have n trials, a vector theta, representing the probabilities of the different possible classes. In this case, it's the different possible words, okay? We have, here I've got A, B, C, D, E, but really it'd be like, I don't know, what's the first word? Aardvark, for the first word, all the way down to, zebra, Z, I don't know, what are some Z words, okay? Zenith and Zizix or whatever, okay? And you got 10,000 of these words, and you got this big long vector, and you're going to spin the wheel a bunch of times or draw a bunch of M&Ms out, and you're going to get, vector of counts here, okay? So that's what we have. I think I left off Monday of last week talking about the Dirichlet. Did I describe the Dirichlet distribution a little bit? So basically, a beta distribution is the conjugate prior for the binomial, okay? Meaning you have these different shapes, and the shape parameters A and B kind of represent pseudo counts of class 0 and class 1. So if your A is 5 and your alpha is 5 and beta is 5, it's kind of like saying, I've seen, from the bag, I've got 2 colors in here. I've seen 5 red and 5 blue. So, what do you think is the probability of red and blue in here? And, based on 5 red, 5 blue, we think 50% is most probable, but because it's a fairly small sample, it could be higher, like 70%, 80%, or lower, 30%, 20%, okay? But if I said, I've seen 500 red and 500 blue, okay, I draw some, then I'm very confident that my bag is really close to 50% red and 50% blue. So my distribution there is a lot more narrow, okay? Whereas if I said I've seen 20 red and 80 blue, okay, now I feel like, okay, whatever's in my bag has got to be pretty close to only 20% red or something like that. It might be a little higher, like 25% red. It could be lower, like 15% red, okay? But I would certainly not expect it to be 40% red or 50% red. If so far I've seen, 20 red and 80 blue or something like that, okay? So that's how the beta distribution works. And the idea here is, okay, now we have something similar for the Dirichlet distribution, okay? Except now I have multiple categories, all right? So now imagine this being filled with M&Ms, okay? And let's say I only have 3 colors, right? I have the, what was it? The America Patriotic M&Ms. Right, you have this, the red, white, and blue. Okay. This just feels weird. Okay. But, and you want to know, okay, what proportion in the bag are red, are white, and blue? Okay, it's not a clear thing. It's opaque, so you can't really see, okay? And then so, again, maybe you've drawn a handful of, say, 6 M&Ms, and you got 2 red, 2 white, and 2 blue. So at that point, you're thinking, okay, around 33% red, 33% white, 33% blue, but also could be much higher or much lower just because you have a small sample size, right? If you've drawn a bigger sample size and you only got, say, like 2 red, and you got 6 white and 12 blue, okay, now you feel like there's not a lot of red, there's a middle-ish amount of white, and a high amount of, say, of blue, okay? Because I don't know, so 2, 6, I don't know what this adds up to, but basically you have these kind of different probabilities, kind of representing like what you might believe being here, but also you have this kind of thing. And so when you get a random draw from here, okay, you're going to get 3 numbers. Something happened. Okay, you're going to get 3 numbers that add up to 1. Okay, maybe like 0.12, 0.31, and 0.57, or 0.09, 0.28, or 0.63, or something like that. Okay, so you're going to get a random draw based on that. And so this is how it goes. And just we're going to just generalize this, or just expand this. So instead of 3 words or 3 categories, now we have a vector of like 10,000, where each one represents, one of the different words in our vocabulary. Okay, does that kind of make sense regarding, I guess, the connection between the binomial and the beta distribution, and then now the multinomial to the Dirichlet distribution? Okay, so let me give you your first answer. First answer is the letter A. A as in apple. What's going on here? Sorry. All right, and let's work through. So I've written this code up. It's in Brew and Learn under week 9, and it says Gibbs Clustering Manual. But this is how we're gonna run this. So just to keep this very, very, very simple, I'm using text from 2 children's books. We have Go Dog Go and Green Eggs and Ham. And so Green Eggs and, I don't know, do you guys know these books? Maybe, like if you're American, probably, but if you're international, maybe not. Not American. I want to go to Amazon, not American Airlines. Okay. All right. So you have Green Eggs and Ham. So this is like a classic children's book, okay, by Dr. Seuss. Theodore Geisel. It's like, if you go to UC San Diego, like he gave a lot of money to them. Okay. Anyway, the story behind Green Eggs and Ham is that he had like his publisher said, I don't know, there was some kind of challenge, and basically he said, I can write a book with 50 unique words. And so if you go through the book Green Eggs and Ham, there's a lot of kind of word repetition, okay? And there's only 50 unique words because the whole book, I don't know if you can read this, is stuff like it says, I am Sam, Sam I am, that Sam I am, that Sam I am. So far we've only had four words, but going along with the pictures, there's already like a story developing, okay? And there's these two characters. One guy is Sam and the other guy is unknown, but Sam is trying to convince the main character, our protagonist, to eat green eggs and ham. The spoiler alert, he protests, but in the end he relents and he says it. And in the end, he says, hey, I like green eggs and ham. All right, so, okay. It's great, okay, right? Would you like green eggs and ham? I do not like them, Sam I am. I do not like green eggs and ham. Would you like them here or there? I would not like them here or there, right? There's this nice rhythm. And then it just kind of keeps going, right? Would you eat them with a fox? Would you eat them in a box? I would not eat them with a fox. Or I do not like them with a fox. I do not like them in a house. I do not like them with a mouse. I do not like them here or there. All right. So anyway, that's green eggs and ham. There's, very kind of set vocabulary there. The other book that I've turned into documents here is Go Dog Go. And this is another classic. Why can't we look at the pages? Please, I want to see. All right, so anyway, in Go Dog Go, there's... Oh, you can hear an audio sample of it?
Little dog. Big dogs and little dogs. Black and white dogs.
Okay, all right. This is a little bit too slow. But yes, the text for Go Dog Go is, dog, big dog, little dog. And there's pictures to go along with every single one of these things, right? Big dogs and little dogs, black and white dogs. And then there's these two characters that keep showing up. Hello, hello. Do you like my hat? I do not like. I do not. Goodbye. That's about like my conversations with people as well. All right. And then there's a whole bunch of things, right? Like the sun is up. The sun is yellow. The yellow sun is over the house. It is hot out here in the sun. It is not hot under here. Hot here under the house. Okay. So anyway, these are our documents, and basically I've just taken the text from the book and I split it up into like 9 chunks, and this will now form our documents, okay? And so I'm gonna read in a couple packages. Text mining and Snowball are kind of these text processing things, and I'm gonna just read in the text from Green Eggs and Ham and Go Dog Go. And then what we're gonna do is I use these functions that will basically turn these documents, okay, these words of text into our vector representation, okay? Basically a bag of words model. And so I'm going to do this. I do a few text processing things like make everything lowercase, I remove the punctuation, I remove the word numbers, and then I'm going to remove the English stop words, okay? English stop words are words that carry little contextual meaning. We need them to make sense. So these are basically articles, all of the to be verbs, things like that. So things like it is gets removed, the, a, prepositions of, those all get removed. So basically we're just left with nouns and verbs. Okay, so I'm going to do that. And so, for example, we can kind of inspect and see what the bag of words look like for one of these documents. So if we look at, okay, and then the other thing I did was called stem the words, okay? So document 4 is this one, which is, I do not like them in a box. I do not like them with a fox. I do not like them in a house. I do not like them with a mouse. I do not like them here or there. I do not like them anywhere. I do not like green eggs and ham. I do not like them, Sam, I am. And that gets turned into, if we remove all of the stop words, okay, so the words I do not all get kind of thrown out because those don't convey a whole lot of meaning. So the entire document gets reduced to like box, like fox, like house, like mouse, like anywhere, like green eggs, ham, like Sam. Okay, that's this document. We see mouse is spelled without an E, and anywhere without an E, and house also without an E, and that's because the stem words kind of like find the roots of the words, but not exactly. You have like related words like house and houses and housing, and those would all get reduced down to HOUS, okay? And then I think mouse and mice get reduced to MOUS, and I don't know, is there a verb form of mouse? I don't know, okay? Mousing around? I don't know, so. Well, anyway, mousy. I guess you might describe somebody as mousy. I don't know, whatever. They get, we stem that, right? I don't know. It's a little strange, but that's what we have. And, if you wanted to, say, inspect the next document, where it says a train. Would you on a train? Not on a train, not in a tree, not in a car. Sam, let me be. All right. And that gets reduced down to train. Car, Sam, let, box, fox, will. Okay, anyway, that's what we have there, okay? So this is just some text processing stuff. The thing about Go Dog Go, we're looking at, I think, where is it? This one, okay. Hello again. Hello, do you like my hat? I do not like that hat. So now it becomes hello, like hat, goodbye, dogs and cars, dog car, go away fast. Okay, so this is what we have, and then we turn them into document counts. Okay, so we have looking at these two things. We have a total of 59 kind of unique words across the two books because we've thrown out a lot of the stop words, okay? And we can kind of, take a look. So, for example, let's look at, so if we take this one, like box, like house, this one, and if I inspect that document, we'll look at row 4 and maybe, okay, this is the resulting kind of vector representation. Like shows up 8 times, okay, so this is document 4, and then we have anywhere once, box once, egg once, fox, green, house, ham, house. Like shows up 8 times, mouse shows up once, Sam shows up once, okay. If I go to, say, document 15, which was about the dogs, I might need more words here. Let's see. Okay, well, it just gives us a few of them, okay? So things like away shows up twice, dog shows up 5 times, goodbye, green, these show up. So we get, document counts for each of these things. So this is kind of what our document term matrix looks like, okay? And so we have 19 documents. If I look at any of these things, word counts directly in the matrix form, okay? So this is anywhere, egg, green, ham, like shows up 8 times, right, okay, and then where the Go Dog Go, okay, so egg shows up 0 times, but green shows up once, because I think in this one, where is it? Okay, So here, it says the light is green now. So green does show up, okay? Green shows up one time, like shows up twice. Do you like my hat? Dog, goodbye, hat shows up, hello, things like that, okay? So we have basically kind of word counts for each of these things, and the challenge is based on what words you see, okay, just the numeric count. So actually it doesn't even know the words. It just knows like, okay, this is column 1 has a 1 in it, and column whatever 59 has a 0 in it, okay? And over here we have column 1 has a 0 in it, column 59 has a 0, but column, whatever this is, column 5 has a 2. Over here, column 5 has an 8 in it. And based on what counts appear in each of these columns, can we start to cluster them? So we use the Gibbs sampler here, okay? So I'm going to kind of just set up some initial hyperparameters, which the idea here is we're going to just randomly draw, okay? We're going to randomly sample a 0 or a 1 by flipping a coin, okay? And then what we do is we kind of count up all of the words that currently have a 0 label and currently have a 1 label, okay? We count all of those things, and we just use those as kind of the priors in our Dirichlet distribution. And so using that, we establish kind of our word counts for everything that currently has a 0 and everything that currently has a label 1. Right now it starts off randomly assigned, and then we just say, hey, let's take this one document out, okay? If I remove, say, document 4, which is this one, hello again, or whatever, document 15, hello again. And if I remove that, what are the word counts of everything labeled 0 and labeled 1 without including this in? And then we get kind of our Dirichlet probabilities there, and then we will draw a random value here. So here I'm getting my word counts for each document for corpus 0 and corpus 1, okay? And then we're gonna draw, this is kind of getting the probabilities for each of these things, and we just draw one of these words at random from a random Dirichlet. So we're generating a random sample, and we're saying, hey, give me the probability for kind of our word counts using document 0 and document 1. So I'm going to go ahead and I'll run this, and that's it. So because our vocabulary and everything is so simple, it starts off, it converges basically like very quickly. So here, so what this represents, so we have 19 documents, okay? I have 10 documents from Green Eggs and Ham and 9 documents from Go Dog Go, all right? And so the correct classification is at the end, we want the first 10 to be 1s and then the remaining 9 to be 0s. And right now we have one misclassification right here. But in the beginning, we just started off with random assignments. I just flipped coins and I said, some of these are going to be document 1s and some of these are going to be document 0s. So in the beginning, it was kind of like very wrong, all right? But then, so I said, all right, make a corpus where, your first document is, I am Sam, this and that. And we just kind of clustered them, right? We just kind of had these things and we kind of created 2 piles, and I said, all right, look at this pile. Tell me how many times you see green, how many times do you see egg, how many times do you see ham, how many times do you see dog? And I say, here's the other pile, how many times do you see that? And it counted them all, and then I said, okay, now let's remove this one document. Okay, now, count up how many you have in this pile, the words in this pile and the words in this pile. And then based on those counts, we kind of classify this, all right? And we use kind of a random thing using the Dirichlet. And then we kind of reclassify it. So at the second iteration, this is kind of what we get, right? So just kind of resampled each of these things. There is some randomness here, but each time it kind of improves a little bit. And eventually, kind of like by the time we get to our sixth iteration, we have it almost all correct. We just have this one document, document 14, which is this one. This one, for whatever reason, is getting classified, has a hard time getting classified correctly. I don't know. The sun is up, the sun is yellow, the yellow sun is over the house. For whatever reason, this one has a little bit of a harder time getting classified. But then by the time we get to, by the end, these are all classified correctly, okay, or clustered correctly. And again, we only know it's correct because like I generated the data, okay, but it says, yeah, these 10 belong together and these 9 belong together. But it does look like it is clustering the documents correctly. So that's, that's a good sign, okay? And so this is kind of how it goes about doing this, okay? So anyway, this is, I guess, just a silly example-ish, but it, when we talk about using the Gibbs sampler and these hierarchical models, sometimes it's a hard time kind of thinking of like what's a broader application of this, and if you can kind of think a little bit creatively, right? So we're accustomed to just working with generally small vectors, but if you say like, hey, you know what, these will work for any size vector, and we're just turning our vector into something much bigger, right? Like something that encompasses the entire English vocabulary of 80,000 words or 10,000 words or however much we want. Okay, and just for a computationally simple example, we have a vocabulary of 59 words, but if you kind of expand it to that, then you have a lot of kind of creative applications here. And so anyway, I recommend kind of taking your time and reading through the article. You can kind of read through the code I have as well, and work through that. So, but yeah, I'm not going to put this on the exam. So, yes, question.
Is this still considered like an unsupervised approach?
So we're not generating the data. We are generating random samples of possible classifications. So, but it is unsupervised. It is unsupervised. So we're bringing in the data, okay, which is these words, and then we are randomly generating a label, okay? But the way we're generating the label is the probabilities, it's conditioned on the word counts. So, we say, what do we think is the probability that it's a 0 or 1? And towards the end, the probability that it's a 1 is much higher and the probability that it's a 0 is much lower. So when you flip the coin, it ends up being a 1, okay? But it's kind of, based on, what you believe, I guess, is in the contents of the bag and things like that. Okay, I guess I'll give you your last two view quiz answers, and those are the answers C and E. C as in cat, E as in elephant. Okay, we'll wrap things up here. Have a great rest of your day. We'll see you Wednesday.